Liangzu Pen. I'm very excited to talk about the convergence of the iteratively revealing square algorithm for outlier-robust estimation. In this estimation problem, we are given data points d1, d2 up to dm, and we want to minimize some outlier-robust loss rho composed with some residual function r in variable v subject to constraint c. Because rho can be non-smooth, we are going to employ the graduated non-convexity framework, that is to construct some smooth surrogate rho epsilon of the original loss rho. Rho epsilon is designed such that as epsilon goes to 0, it recovers the original loss rho. Our contribution is to prove that the IRLS algorithm combined with GNC is a convergent algorithm indeed. In the next few minutes, I will talk to you about more details. Thank you very much. I talked very quickly about the three important notations: outlier-robust estimation, graduated non-convexity (GNC), and the iteratively related square algorithm (IRLS). Next, I will introduce them in more detail. First of all, outlier-robust estimation. In this estimation problem, we have a residual function on the left and the outlier-robust loss rho on the right. So for the residual function, you have two parameters. V could be some geometric parameters like camera relative pose, and di is some data samples as your input, which could be correspondences from two images or point clouds. For example, in linear regression, you have di, your I sample, to be xi and yi, two quantities. And the residual is going to be the distance of this quantity as measured by the absolute value of the inner product of xi and your variable v minus the scalar variable yi. In the case of point cloud registration, your uh, data di is going to be a pair of points xi and yi. Here I'm abusing the notation, and your variable v is going to be a rotation r and a translation t. In this case, your residual is the distance, Euclidean distance between one point yi and the transformed version of the other point xi transformed by rotation and translation. And finally, in the case of essential matrix estimation, you have your data di to be again a pair of two points xi and yi. They are homogenized image coordinates, and your variable v is going to be something called essential matrix denoted by e. And your residual function is the absolute value of a bilinear term xi transpose e times yi. On the right hand side, we have the outlier robust loss rho. We have three examples to show to you. One of them is the LP loss. It's in the picture I'm showing you the case p equal to 0.25. The second loss is called the so-called GM loss. It is the squared residual divided by 1 plus the squared residual. The third example is called the truncated least squares loss. It is the minimum of the squared residual and the square of some parameter c. The common feature of these three losses is that they do not penalize large residuals too much, or if ever. And then that's why they are outlier robust. But the challenge is that the resulting outlier robust estimation problem can be non-smooth and non-convex. There is then a classic algorithm to solve it, like it is called iteratively related squares. The algorithm goes like this: it initializes some variable v0, and it performs alternative minimization. In the alternative minimization, it performs weight update, which is to set a weight to be the derivative of your outlier robust loss divided by your residual. And the variable update instead is to solve a weighted squares problem. The weight update can be typically done in closed form, and then we assume that the variable update can be done efficiently. Therefore, we can run this algorithm. However, this algorithm might not be well defined if rho is not differentiable, which we will adjust this case later. But the challenge here is that for the non-convex case and non-smooth case, how can we prove the correctness of this algorithm or convergence of this algorithm? And to address, first of all, to address the non-smoothness, we consider the graduated non-convexity framework. This is to construct some smoothing surrogate rho epsilon of your original loss rho. The idea is that rho epsilon is constructed such that as rho epsilon goes to zero, you get the original loss. Therefore, we can minimize rho epsilon instead of rho, and then we decrease epsilon, and then we repeat. Therefore, to integrate this GNC idea into IRLS, we write down the following algorithm. It has two major changes in the denoted in the box. First of all, in the weight update, we do not take the derivative of rho, but then we take the derivative of rho epsilon t. And then epsilon t here, we call it a smoothing parameter, and then we will decrease it at each iteration. Of course, the algorithm is becoming more complicated. The challenge remains, which is to prove the convergence of this combination. And this is the main contribution of our paper. Our theorem reads like this. Under minor conditions, we can show that the IRS algorithm and the GNC algorithm, their combination converges eventually to some stationary point. And secondly, the IRS algorithm converges at a sublinear rate as shown in our very recent archive paper. Finally, in our CVPR paper, for a very specific case of linear regression with the LP loss, GNC and LS converges at a linear rate if p equal to 1, which is very fast. And it is even faster for the case p is between 0 and 1 because it converges at a superlinear rate. Do come to our post session for any discussion or comments or suggestions. Thank you very much for listening.